FPGA programming employs two main resources: lookup tables, or LUTs, and flip-flops. We already talked about LUTs in the video about combinational logic. This time we'll talk about flip-flops. What defines combinational logic is that the outputs depend only on the inputs. Non-combinational logic, by contrast, may have an internal state that affects the outputs. Storing this state is what the flip-flops are for. Simplifying things a little, a flip-flop is a single-bit memory unit. Before we talk about how we use it, however, let's try and understand how it's even possible. How can we build a logic circuit that remembers? This is an SR latch, the SR standing for set reset. It has two inputs called, surprisingly, set and reset, and two outputs called Q and Q bar. It is illegal to set both inputs to 1. Under all legal conditions, the two outputs will be the opposite of each other. Inside the latch, there are two NOR gates. Importantly, these gates connect in such a way as to create a loop. The output of one is connected to the input of the other and vice versa. This is what facilitates the memory. When we input 1 on the set line, the top OR goes to 1. Since the NOR is an OR with a NOT on the output, this means the top gate actually goes to 0. Since the reset line is 0, the bottom NOR gate gets two 0 values and outputs a 1. This means that when we input a 1 on set, Q becomes 1 and Q bar becomes 0. If we then input two 0 values, the bottom gate still outputs 1, which means that the top gate still receives a 1 input and still outputs a 0. The bottom gate is still getting two zeros and still outputs a 1. Despite the inputs being neutral, the latch still has Q set to 1 and Q bar set to 0. We have implemented a memory unit. The symmetric design of the latch makes it fairly easy to see that if we set reset to 1 and then back to 0, the latch will output 0 on Q and 1 on Q bar. The next latch we'll look at is called the D latch, or data latch. Essentially, it just takes one input and feeds it to both set and reset inputs of the SR latch. Of course, as shown now, this is just a particularly convoluted method for implementing a line that just transfers the input to the output. Kind of pointless. To make this a little less pointless, we'll add an enable or E input. When that input is 1, we have our pointless transmission line, but when that input is 0, the latch will continue to output whatever value it has last seen before the latch was disabled. Any further changes to the D input will not affect the output until E turns 1 again. Which finally brings us to flip-flops. The main difference between a flip-flop and a latch is the time in which it is sensitive to its inputs. While the latch is sensitive as long as the enable line is 1, a flip-flop is only sensitive during the transition of the input from 0 to 1. Technically, this is done with an edge detection circuit that is only 1 during a short period after the 0 to 1 transition. At this point, you might legitimately wonder what this is good for. I mean, if we're only interested in a short while after the transition, shouldn't we just make sure that that's when we're enabled? The answer is that for flip-flops, this input isn't called enable. In fact, a typical flip-flop will actually also have an input called enable, which will behave precisely as it does with the latch. But this input, the one that triggers latching the data input only during the transition, has a different name. It's called a clock. On the schematics, it's indicated by a small triangle inside the flip-flop's body. Being sensitive so long as a line is 1, or for that matter 0, is called level trigger. Being sensitive only to the change is called edge trigger. So a flip-flop is a latch that is based on an edge-triggered clock. So finally, this is a D flip-flop. It has data and clock inputs and the expected Q and Q bar outputs. It also has an enable input. If that's 0, the D input doesn't affect the flip-flop state even during a clock transition. Last, it has a reset input. This can set the flip-flop to a known state even if there is no clock. So why? Why create edge trigger latches? Flip-flops make a lot more sense if we zoom out and look at the circuit they are typically used in. In particular, let's look at one common use case. This is a sequence of combinational circuits that are fed from flip-flops latching the value of other combinational circuits. As the clock arrives, the intermediate results are latched and the next phase logic takes place. This phased advance of the data through the circuit reminded someone of the way a heart beats, hence the name, systolic circuits. As usual, we'll focus on programming the FPGA using System Verilog. Other HDLs have similar constructs, though syntax will naturally vary. The task we'll want to achieve is to blink an LED at 1 Hz. Naturally, the first step is defining a top-level module in which our LED will be an output signal. We'll also need a clock to work with. Our board provides a clock, so we'll define an input signal to receive it. Of course, we can use combinational logic to hook up the clock input to the LED output, resulting in a contender for the world's most boring FPGA design ever. Before we synthesize this, however, we need to define the constraints. Unlike the previous video, where the pin numbers were conveniently printed on the PCB for us to pick, this time we need to dig into the documentation a little. The most important tool we have is the development board schematics. The schematics themselves contain blocks representing the components on the board and lines representing the connections between them. If we zoom in on the schematics to this area, we see a component labeled SG8002JC. This is the oscillator that produces a clock for the FPGA. The schematics label it Y1, which allows us to find it on the board itself. Back to the schematics, we see that leg 2 is connected to those antenna-looking lines representing ground. Leg 4 is connected to the power supply. In electronics, when specifying voltages, it is sometimes customary to replace the decimal point with the V letter. We thus conclude that the clock is connected to the 3.3 volts power supply. We also see a capacitor between the 3.3 volt power and ground. This is called a bypass capacitor and is meant to increase the stability of the power fed to the clock. Almost all components will have one next to them. The clock gets a 100 nanofarad capacitor labeled C23. This labeling allows us to find that very same capacitor on the actual board, and indeed we see that C23 is right beside Y1. Leg 1 of the clock is labeled OE, which stands for Output Enable. It is connected through a 4.7 kilo-ohm resistor to the power, which puts it at high state. This means that the clock is set to always output. We can also see resistor R16 on the board, and the markings on it, 472, mean that the first 2 digits of its resistance are 4 and 7, and these are followed by 2 zeros. In other words, this is a 4700 ohm resistor, just like the schematics mandate. By the way, this connection of a logic input to power is called a pull-up resistor. Which leaves us with leg 3, labeled out. That's where the actual clock square wave signal is produced. The line connected to this leg is cut short, but it has CLK50M printed above it. What happened here is that, to keep the schematics readable, the wire is not fully drawn out. Instead, this wire has a continuation somewhere else in the schematics. That wire will be labeled with the same label. Since this is a PDF, we can simply search for CLK50M. We find the other end of that wire connecting to a chip labeled U1B. U1 is the FPGA itself. Furthermore, we see that the wire connects to leg H13 of the FPGA. This gives us everything we need in order to write the constraints needed for the clock. We now know that the clock leg connects to package pin H13, and we also know that it needs to be set to 3.3 volts. If we search for LED, we soon find the triangle line and arrows that mark a light-emitting diode. Here we see that the board has 4 LEDs marked D1 through D4. D1 is connected between 2 resistors. We also see a wire labeled FPGA done. Following that lead, sorry for the bad pun, we see it connects to the FPGA to a pin called done 0. This is not a programmable pin. It indicates that the FPGA has a design loaded into it. In other words, this LED indicates the FPGA is programmed and is not under the specific design's control. As a side note, the 2 resistors serve 2 different purposes. R19 is a pull-up resistor designed to make sure the LED is on if FPGA done is neutral. R26, however, is a current limiting resistor designed to make sure the LED doesn't consume too much power and burn. Now, don't get me wrong, they are both standard 1 kilo-ohm resistors. It's their use rather than the resistors themselves that makes this distinction. D4 is even stranger. It just connects the 3.3 volt power through current limiting resistor R23 to the LED and to the ground. This LED just indicates that the board is receiving power and is not under the FPGA's control. That just leaves us with D2 and D3. They are connected to 3.3 volt through a current limiting resistor, but the other side is just a wire, labeled LED D3 for D3 and, confusingly, LED D4 for D2. Looking at the layout on the board, with D1 being next to D4, it's obvious that someone somewhere simply made a mistake or started reordering and never finished. Either way, we see that LED D3 connects to the FPGA to leg M10 and LED D4 to leg E11. We'll control D3 for this design, so we'll connect our LED signal to M10. We likewise see that we need to set the voltage levels to 3.3 volts. And with that, we're done. We can load the design on the board, and we see both D2 and D3 faintly glowing. While they seem to be in the same state, they are not. If we look at D3, which is the LED we programmed, with an oscilloscope, we can see a 50 MHz 3.3 volt wave on it. It doesn't look very squarish, but that's how things look in the real world. On D2, we see no such wave. It's at a constant voltage. In other words, the reason D2 is faintly glowing is because we didn't tell the FPGA what to do with it, so it kind of defaulted to this state. D3, on the other hand, is faintly glowing because the clock is a 50 MHz clock, which is way too fast for us to see blinking. Fixing D2 is easy. We'll just define an output for it. Due to the way the LED is wired, it is on if we output a 0. So if we want it off, we need to output a 1. Set the output pin to E11 and the output voltage to 3.3 volt, and we should see it as a constant off. All of this is fine and well, but we want to be able to see D3 blinking. We need to slow it down, by a lot. In other words, we need a frequency divider. These work like this. We take a counter. Every time we see a clock, we increase the timer. When it gets to our divider number, we reset the counter and change the state of the LED. The first thing we need is code that runs when the clock goes high. In System Verilog, this is done with the always FF block, FF standing for Flipflop. We need to tell it which event to look for. In our case, we want the positive edge of the clock signal. This part is called the sensitivity list of the block. Logic-wise, what we write here will only take effect when the clock transitions to high. Next, we need a counter. Since our input clock is 50 MHz and we want a 1 Hz output, we need a counter with enough bits to count up to 50 million. We could calculate precisely how many bits we need, but for now it's simpler to just use 32. So I'll define a 32-bit packed array of reg variables. Each such reg variable represents a single flip-flop. I'll define a parameter called frequency divider and we'll set it to 50 million. It is slightly easier to use a count down rather than a count up timer, so we'll set the initial value accordingly. Which brings us to the actual timer. Essentially, what we need to do is assign to counter the value of counter -1. Right away, you will notice that this was not possible with combinational logic. There, we could not have a variable reference itself. That would amount to a loop in the logic, which is not allowed. For one thing, such a line, if written in combinational logic, would run at an unknown rate. Here, however, this line only executes once per clock. To denote this difference, we're using a different assignment operator. The regular equals assignment operator is used for combinational logic and is called blocking assignment for reasons that I prefer not to repeat because I personally find them more confusing than helpful. Another name, which I find more helpful, is continuous assignment, but sadly this name is less commonly used. The lesser than equals operator is called the non-blocking assignment and can only be done with variables that can be turned by the synthesizer into flip-flops. This one is also sometimes referred to as procedural assignment. When running in a simulator, pay attention to visibility. Blocking assignments immediately show up in the variable's value. Non-blocking assignments only take effect after the clock edge. That is actually the reasoning behind the naming. With that said, I advise you not to overly rely on that effect, lest you end up with code that works only in the simulation, not on a real device. If you don't know what any of that means, don't worry, we'll get to simulation in some future video. Either way, simply running the counter isn't enough. We can now test whether it's 0, and if so, reset it. At this point, we should also switch the LED's state. Except this doesn't work. LED is just an output signal, which means we cannot non-blocking assign to it. At least in System Verilog, we can read from it. In Verilog, we couldn't even do that. To fix this, we can add the keyword reg to the signal's definition. We should also give it an initial value. Of course, now that it's a register, i.e. flip-flop, we cannot use the assign keyword on it. Assign has the same effect as continuous assignment, which is not allowed on flip-flops. Since we don't need that line anyways, we can just delete it. It takes almost a minute to synthesize the design, but once we're done, we can load it. We finally get our blinking LED. Cool. Except there's a problem. The LED is blinking too slowly. Instead of blinking at 1 Hz, it's blinking at half a hertz. Instead of turning on and off every second, it's on for a second and then off for a second. The reason for that is we got our math wrong. Our input clock runs at 50 MHz. This means it has 50 million rises and 50 million falls each second. We're dividing that by 50 million, but we're only counting the rises. We completely ignore the falls. This means that by merely putting pause edge into our sensitivity list, we have an inherent division by 2. As such, we need to divide by 25 million, not 50 as we did. Thankfully, that's easy enough to fix, and we now have a 1 Hz blink as we wanted. Except that's still not 100% true. The error is too small to show up on the scope of this resolution, but we have an off by 1. We do not flip the state of the LED every 25 million cycles. We flip it every 25 million and 1 cycles. Our frequency is ever so slightly too low. I've actually already given you everything you need to figure out why, so feel free to pause the video and try and figure it out. I'll wait. Got it? Well, here it is. At line 35, we update counter to decrease by 1. But this is a non-blocking assignment. When we read the value of counter at line 37, we're not reading the updated value. We're still getting the value before the update. So at cycle 0, we load counter with 25 million. At cycle 1, we decrease it to 24,999,999. At cycle 24,999,999, we decrease it to 1. At cycle 25 million, we decrease its value to 0. But when we read it at line 37, we still get 1. So we do not activate the if. We only activate that at the next cycle, which is cycle 25 million and 1. Then we set it to 25 million again, which is cycle 0 of the next phase. Our LED cycle is not at 1 Hz, but at 0.999998 Hz. Granted, at these division levels the difference is not very significant, but your typical divisions will be much smaller, which means the error will be much higher. There are multiple ways to deal with this, but the simplest one is to just compensate for this in advance. If we set the frequency divider accordingly, we can keep the rest of the code as is. When developing for FPGA, I find it very illuminating to look at the logic that our code produces. So here we can see the tying high we did to that other LED. Over at the main path, we see the clock coming in and being routed to the clock input of the LED reg flip-flop and to the cluster of flip-flops that compose the bits of counter reg. Following the LED register, we see that the output, in addition to being fed to the LED output, is also routed back to a NOT gate and back to the data input of the flip-flop. As is, this means that every cycle the LED output will flip state. However, the enabled pin of the flip-flop is also routed, which means that on most cycles it will be low and the new input will not be activated. Going backwards to the design, we see that the enable pin is routed to a ROM. The comparison to 0 is implemented using lookup tables that appear as a ROM in this representation. This is also why our quite modest design takes up 39 LUTs. At the end of this video, I'll show you how to dramatically reduce this count. We can see that what's being fed into the ROM is the output of the counter register. That, in turn, does not have a visible enable input because we unconditionally update it every cycle. The content of what we update it with changes, but the update happens every cycle without fail. Which brings us to the input of the register. This trapezoid is the symbol for a multiplexer, often referred to as a MUX. It has a selection input at the bottom and multiple data inputs. Based on the selection input, it routes one of the data inputs to the data output. The two options are hex value 17D783F, which in decimal translates to 24,999,999, or the result of a component that subtracts 1 from the previous value of counter. Here's what I want you to take away from this. Despite the fact that our code only had an always FF section, there is quite a bit of combinational logic going on here. The comparison ROM, the MUX, and the sub node are all async. If we were to watch this circuit in operation, we'd see each cycle the counter changing, followed by the ROM, subtractor, and MUX changing sometime after the clock. Then everything would settle down until the next clock, at which point this all happens again. Every so often, the ROM would issue a 1, which would mean that the next cycle the LED register would also change. This means that, when designing, you need to keep an eye out on resource usage. Every logic step takes resources. It also takes time, but that's for another video. I'm also ignoring the critical warnings reported for this design. Generally speaking, critical warnings should never be ignored, but this design is simple enough and for educational purposes only, so we'll let it slide. There's one more functionality I wanted to add. We might want to be able to reset the whole thing. The board has two programmable buttons, and one of them is even labeled N reset. If we look at the schematics, we see that it is pulled high to 1.5 volt when the button is not pressed and connected to the ground when it is. So this signal will give us a 1 if not pressed and 0 when it is. We also see that it connects to the FPGA to port F4. So we'll add to our design another input called N reset, the N meaning negative, active low. We'll set the constraints for it to 1.5 volt operation and port F4. All we have to do now is add it to the always block. As far as logic goes, we could just sample the input when the clock arrives. After all, a button push cannot realistically happen faster than the interval of a 50 MHz clock. I don't want to do that, however. I want the reset button to have an immediate effect. We can do that by adding it to the block sensitivity list with a comma, neg edge, and reset. We then can perform an if on it, and if it's 0, reset the LED to 1, off, and the counter to the start value. And then the rest of the code goes into the else clause of the if. If we synthesize and load, we see that indeed, pressing the reset resets the behavior. Good. I promised to show you how we can reduce the resource usage of the design. Before I do, however, I'd like to remind you of the existence of my Patreon page. Please consider supporting this channel. Links and credits are available in the description. Thank you. The schematics we're seeing now on screen are a result of an RTL analysis. If we look at what was actually produced by the synthesis, they look considerably less clean. The first thing we can do is reduce the number of bits we store the number in. After all, 32-bit can count up to 4 billion. We only need 25 million. Verilog provides a compile time function that does a ceiling, or rounding up, of the base 2 log of a number, which coincidentally are the number of bits we need to represent that number. So all we have to do is use that function, called clog2, to calculate how many bits we actually need. Since packed array bounds are inclusive on both high and low end, we range it from frec_div bits -1 to 0. Synthesizing, we see we have reduced our flip-flops usage from 32 to 26 and the latch usage from 56 to 45. But we can do even better. So far we've been subtracting 1 from the counter until it reaches 0. If we subtract 1 more, we will have a negative number. We can expand counter by 1 bit, so it has 1 bit above the number of bits strictly necessary to hold the frequency divider. The way 2's complement numbers work, this extra bit acts as the sine bit. It will turn to 1 when the counter turns negative. So now, instead of comparing all the bits of the counter to 0, which requires a lot of logic, we need only test 1 bit. If it's set, it's time to reset the counter and flip the LED. Of course, this also means we've added another extra cycle to our run. So we need to adjust the reset value accordingly by subtracting 2 instead of 1 from it. Our flip-flop use rose from 26 to 27, which is to be expected. Our latch use, however, dropped from 45 to just 28. For most design, that's a very good trade-off to make. And that's all for this time. Thank you for watching.